Assalamualaikum all. I'm just in Ottawa here at the Equators Coffee Roasters. Actually, this was started by one of my friends who was also a math teacher. And I'm picking this particular spot. There's a lot of traffic here out in the east, always. So if you can't hear me too well, it's kind of typical. I'm picking Equator Coffee Roasters. It's local, but more specifically, one of the intentions that they had when they first started opening up these shops, and there's a couple of them in the city, is to be environmentally aware and environmental stewards, right? The owner was a scientist, like I said, he was a math teacher, but also a scientist as well. And he was very well aware of all the plastic consumption and production and the effects that it has on the environment. And so this is one of the coffee shops in particular that really pays attention to make sure that all the cups and bags and even muffin wraps that they use are biodegradable and still organic compounds, but really processed in a different way. So it's kind of an insight into the useful applications of the processes that we're going to talk about in this video. But I'm kind of showing you this because there is a point where science has to beat humanity, right? And as a scientist myself, sometimes we lose sight of that, right? The purpose of science is to serve. The purpose of everything that you're learning is really to serve. So let's look at the processes that make all the things such as coffee cups and paper bags and all that stuff. And take a look at what goes into that. So what we're going to look at is the reactions that actually happen inside the tower. One of them is thermocracking, and that's where we use heat as the primary agent to break the larger compounds into smaller compounds. This can be any larger compound, it's nothing specific, but if I look at this example here, I have what we would call something like an octane. And so with heat, I take that octane and I break it into 2 or more different compounds. In this case, I'm breaking it down into a butane with 4 carbons and a propane with 3 carbons. And sorry, it's actually a heptane, not an octane in the beginning. The point is that they are 2 smaller compounds. Even more so, or even more general, I should say, is that we take the larger molecule and we're breaking it down into smaller molecules. Now, this doesn't have to always be 2 as well. In this example, we do break it down into butane and propane, but it can be more than 2 as long as the equation is balanced. So when we're drawing these reactions, the thermal cracking specifically, there is a couple of key things to remember. One is that the products can be really any combination, okay? And of course, it has to be an organic compound. But as long as the sum of the carbons in the products equal the amount of carbons in the larger molecule from the reactants, it should be able to work out. So in the previous example, I did butane and propane, but I could have done pentane and ethane. Okay? The idea, though, is that the products must be smaller, right? As individual monomers, they must be smaller than the size of the reactants. And again, depending on how we've broken it up, it can be done several ways, but the equation must be balanced. So I should not see a heptane break into 2 butanes, because that would mean that there's 8 carbons on the product side and not 7. So it doesn't matter what the organic compounds are, but they must obey the law of conservation of mass. So there may be some cases where we need to add coefficients to this in order for everything to be balanced. The second main reaction that happens inside the tower is something called hydrocracking, where we use hydrogen and usually a catalyst to break again the larger compound into smaller compounds. And the combination doesn't necessarily have to be specific, but the compounds must be smaller. So if I look at this example here with octane, and instead of just using the catalyst, I'm going to add hydrogen, which really breaks down into H and H. Now, that each of those hydrogens are going to attack carbons, a carbon bond that is connected inside the larger molecule. Once they attack and attach themselves to the carbons, they will split that molecule into 2 separate, smaller organic compounds. So in this example, we broke octane down into pentane and propane. And what I've done here in red is highlight where the H's went between the two compounds. The third main type of reaction that happens inside the fractional distillation tower is something called catalytic reforming. And that's where we use catalyst as the main mechanism, of course, where the longer hydrocarbons are broken down into branched benzenes and hydrogen as two separate entities. So if I look at this example here, we have octane, and with the use of a catalyst, it's going to break down into a benzene ring or benzene structure with two branches, and this works because with the benzene structure and the two branches, you have 8 carbons on one side. But, like we said, hydrogen is going to be formed separately. You can think about the hydrogen is essentially being removed when this occurs. And so if I look at the benzene ring separately and I add all the H's, remember that with all these 3 reactions, your entire reaction has to be balanced. That includes the hydrogens as well. So when I label all the hydrogens I've done in red here and I count them up, I will see that I have about 10 hydrogens in total there. Now, for octane, when you apply the formula, we end up having 18 oxygens. So what do you think we're going to have to do to, not oxygens, sorry, hydrogens. 18 hydrogens. So what do you think we're going to have to do to make sure that the hydrogens are balanced? I want you to take a minute and think about it. If you guessed that we'd have to put a coefficient of 4 in front of the hydrogen gas on the product side, that is correct. Now if we add the 10 plus 4 times 2, that gives us 18 hydrogens in total. And again, that is to balance. Now for this next example, we're going to catalytically reform decane by first drawing benzene out. You can use any combination you wish. In this case, I'm going to add an ethyl group and a methyl branch and another methyl. And that way 6 plus 2 from the ethyl plus 1 from the methyl and 1 from the other methyl give us a total of 10 carbons. But remember, any combination can work. And of course, hydrogen is removed. Now, when keeping in mind that all the atoms must be balanced, including the hydrogens, we see that on the side with decane, there's 22 hydrogens. And so once again, when we count all the hydrogens involved in the benzene, we see that there are 14 hydrogens, which means that we're going to need another 8 on the product side in order to balance, and we can do that simply by adding the 4.